So thank you very much. I hope you can hear me at the back. So first of all, thank you very much to Shrikant and to Professor Kamala and all the ICTS outreach coordinators for and staff for organizing this. I have to say I'm very honored to be part of this tradition. In fact, Professor Kamala just told me this was the 2755th lecture in the Bangalore Science Forum lecture series, and I've certainly never ever been part of such a venerable tradition before. So thank you very much for inviting me to give this talk. So I'm going to talk today to you about something that's slightly abstruse. It's about black holes and the reversibility of time, but I'll try and make it as comprehensible as I can, and hopefully if there are questions, feel free to ask me later. If you really have a question, and then you can't wait, you can interrupt me. It might help, but we'll try and keep all questions towards the end. Let's see how it goes. Even though this talk is about black holes, what this talk is really about is about a story of gravity. So before I start talking about black holes, I thought I'd start just by telling you a story about gravity. And the story of gravity actually starts with something that all of us know and have studied in school, and it starts basically with Newtonian gravity. Okay? And so Newtonian gravity, as all of us have followed, was something that was developed primarily to explain planetary motion. So that's where people first started studying gravity. And the Newton's force law is something which is very simple, and it tells us that if you have two objects and they have some masses, then the force between them is proportional to the product of the masses of these two objects, and inversely proportional to the square of the distance between them. So if you double the distance, the force goes down by a factor of 2. You double the mass of one of them, the force goes up by a factor of 2. And this was a very successful principle because it helped initially explain why the planets went about in the orbits that they did. In fact, however, Newton's force law though has a rather large range of validity which goes beyond the original reasons for which it was developed. So if you look here, you try and ask how the moon goes around the earth, and in fact the moon goes around the earth obeying exactly the same force law that the earth obeys around the sun. So sometimes it happens in physics that there is some rule at some length scale and there's some other rule at some other length scale, but in fact Newtonian gravity is something that's valid for a remarkable range of length scales. So if you want to understand why the moon goes around the earth, or why the earth goes around the sun, why rockets go up, of course the motion of a rocket is complicated, but the gravitational force that acts on a rocket is still explained very well by the Newtonian force law. If I throw this up and it comes down, that trajectory is also explained very well by the Newton's force law, and therefore in a sense this is a law that's been with us now for more than 300 years, but it's a rather remarkably successful principle in physics. It's one of the most successful principles in physics, this very simple rule that tells you that the force between two objects is proportional to the product of their masses and inversely proportional to the square of the distance between them. However, in the late 19th century and the early 20th century, physicists realized that there was something slightly unusual about this law, and that was the following question. Okay? So imagine you have the sun and you have the earth, and the sun is exerting its force on the earth, and the earth is exerting a force on the sun. And now imagine that some huge extraterrestrial civilization or some giant, so here's our giant, okay, comes and he moves the sun. Okay. So this is an example of the kind of experiment I'm going to talk about many times in this lecture. It's a thought experiment. Okay. Of course, you don't have giants of this kind, nothing for them to stand on to move the sun. But let's suspend disbelief and imagine that somebody comes along and he pushes the sun a little bit. Okay. So the question is, how long does it take for the earth to know that the sun has moved? Okay, so that's the question that I want you to focus on. So it takes some time for light to come from the sun to the earth. It's about 8 minutes. But if you look at the form of the Newton's force law, that tells you that the force between the sun and the earth is proportional inversely proportional to the square of the distance between these two objects. So when this giant pushes the sun, the distance between the sun and the earth will change. Right? And therefore, if you believed in Newton's force law, you would believe that therefore the force between these two objects would change, and it would change instantaneously. Right? So there's a question about whether Newton's force law really, whether you should take this prediction seriously, which is the idea that if someone comes and moves the sun, then the earth would know about it instantaneously. Okay? Now, if the Earth did know about it, then that would be a method of sending signals arbitrarily fast, right? Because you wanted to send a signal, let us say this giant wanted to send a signal to the Earth and he did not have time to actually go to the Earth. All he had to do, all he needs to do is move the sun, and when he moves the sun, people on Earth know that the sun has moved. Right? Okay, so now in the early 20th century, people found that this was in contradiction with another principle, which was the principle of relativity. And the principle of relativity, which was being developed at the same time, more through a study of electrodynamics than through a study of gravity, tells us that no information can move faster than the speed of light. By the way, this is the Einstein lecture, so it might be worthwhile taking a slight detour into the history of relativity, not a very long detour. But really a lot of special relativity was developed by Lorentz and by Poincaré, and a lot of the results that describe the theory of special relativity were basically developed by these people in the late 19th century and the first few years of the 20th century. And Einstein in 1905, he cleaned up the theory. He wrote a very nice paper which kind of reviewed a lot of these developments and explained how this theory could be derived on some simple foundations. But it's a slightly unfortunate history, because if you read this paper, it's a very nice paper to read, but it doesn't cite any of the work of these people, even though all the results, effectively all the physical results were present before them. So it's an Einstein lecture, and there were indeed important contributions that were made, but it's useful also to keep these other aspects of history in mind. And there were many people who contributed to the history of special relativity. And in any case, what all of these physicists discovered was that on various grounds, you believe that information can't travel faster than the speed of light. And therefore, if you take this prediction of the Newton's force law seriously, which is the idea that the force really depends on the distance, the instantaneous distance between two objects, that contradicts this notion of special relativity. So for this reason, in fact, for many other reasons as well, thinking also about the so-called principle of equivalence, people developed a different theory of gravity, and as Professor Kamala mentioned, this is the 100th year of the development of this theory of gravity, and this is the theory of what's called general relativity. Okay? So the way general relativity works is, you still have the sun and you still have the earth, that's the earth and that's the sun, I hope you can see at the back, but it doesn't say that there is a force between the earth and the sun. Rather, what the theory of general relativity says is that, we invent something which we will call the fabric of space-time, and this fabric of space-time mediates interactions between the sun and the earth. So it's not as if the sun exerts a force on the earth which causes the earth to go around, but rather what happens is that the sun, by virtue of its mass, causes a bump in the fabric of space-time, and then the earth moves in this deformed fabric of space-time, and the reason it goes around in the orbit that it does is not because it feels a force, but rather because these orbits are the natural trajectories to take in this deformed fabric. Okay? So there are some precise equations that describe the mathematics of all of this. These are the equations that tell you how the fabric is deformed in response to matter and how matter moves in response to this deformed fabric. One thing that's actually very important to keep in mind when we discuss all of this is that from a quantitative point of view, the actual predictions of these equations are very close to those of Newton's force law, and that's why it took so long for these equations to be developed. So these equations are the equations of general relativity. In fact, once again, even though it's Einstein who's often associated with them, they were first written down by this person David Hilbert a little earlier than Einstein, and he was the one who first got the correct equations. And the philosophy that goes along with these equations is in fact the idea that matter tells space-time how to curve. Okay? So as a result of the sun being in some place, there is a certain curvature that develops in this fabric of space-time, and then as a result of that curvature that causes some other matter to move in a particular way. So this second equation is the statement that space-time tells matter how to move. Okay? So that's the philosophy of general relativity, and you see that it's very different from the philosophy that you had for the Newton's force law. Okay? And you know, even though, as I said, from a quantitative point of view, the theory of general relativity is very, very close to the theory of Newtonian gravity. You know, it took very accurate observations. It took these very accurate observations of the shift in the perihelion of Mercury, and if you sit down and you do that calculation, you will see it's really a very delicate calculation, and there are all sorts of effects that go into that shift in the perihelion of Mercury that just come from Newtonian gravitational effects, which are far larger than the effects that you get from this theory. So even though from a quantitative point of view this new theory is very similar to the old theory, from a philosophical point of view, notice it's completely different. So this new theory has the property that it's a local theory. So if you were to do an extreme experiment, you know, our giant is back here. So if this giant were to come here and were to do this extreme experiment of pushing the sun, then unlike the Newtonian theory, what the general theory of relativity tells you is that by pushing the sun, you would cause ripples in this fabric of space-time. So you can see these ripples in this fabric of space-time, and the earth wouldn't know instantaneously that the sun had moved. Rather, these ripples in the fabric of space-time would propagate, they would propagate at the speed of light, and so it would take 8 minutes for the light to reach earth, that the sun had moved, and also for the effect of gravity of the sun to change from what it was previously. So you see that even though in everyday experiments general relativity is very similar to Newtonian theory, and that's why we don't usually need to use general relativity in everyday experiments, from a philosophical point of view, and if you start thinking of extreme experiments of this kind, which are in fact the kinds of experiments I'm going to speak about for the rest of this talk, these two theories are very different. And the most important thing I want to focus on, and that's something I'll come back to later, is the difference in the philosophy. Okay, so the Newtonian theory is a theory of action at a distance. It says here are two particles, they act on each other at a distance, and there is some force between them, and that force just acts between these particles. The general theory of relativity is a local theory. There is a field in the middle, which is the field of space-time, and now there is a blue field. and so this maybe if there are questions I can take. Should I take a couple of quick questions or no? No, there's no screensaver.
The space is curvature, sir?
Correct, the space is curved. Space-time is curved, yes. This is a different theory of gravity, you see. So the question is if the theory of gravity still holds. It's a different theory from the Newtonian theory. The Newtonian theory says the force is proportional to the product of the masses. This is a different theory. It's a theory that says space-time curves and then things move in that curved space-time. It gives different predictions from the Newtonian theory, slightly different predictions, but it gives different predictions. So philosophically it looks very different. It's a theory, but it gives quantitatively, it gives very different predictions. But the change in our picture of the universe is very radical. Okay, good. So as I said, the change in our picture of the universe is now completely different. We've invented this fabric of space-time, which is mediating things. And in fact, this is the way in fact all, I would say, all theories of modern physics, at least fundamental physics, work in this way. They always work through fields. They're all field theories, where you have these intermediary things which mediate forces. We don't any longer talk about forces at a distance. Rather, we always talk about fields, and then we have objects that influence those fields, and then those fields that go back and influence the objects in turn. And so general relativity is also an example of a field theory, and therefore it's a local theory that tells you no information travels faster than light. Okay? So I hope this philosophical distinction between the two theories is clear. Okay, so in fact, when people started examining these solutions some more, in about 10 years after the equations of general relativity were first found, a German mathematician called Schwarzschild found an exact solution to these equations. So these equations, were complicated equations, and people had tried to analyze them, but they didn't really have exact solutions to them. They're very complicated equations even now to solve and understand. but the German mathematician Schwarzschild found some exact solution to them. The form of the solution is not important, I am not going to use, so do not get scared by the equation. I just want to show you that there is some kind of solution you can write to these equations, and this solution is written in terms of a distance function on the fabric of space-time. So, what it says is, if you have some point here in the fabric of space-time and some other point here in the fabric of space-time, what is the distance between them? And if I tell you the distance between all sorts of points on a surface, then that tells me the geometry of the surface. So, this ds squared is a length element between 2 points that are separated by a very small amount in coordinates. And this tells you how the distance, you can integrate this to get the distance between 2 points that are separated either by a small or a large amount. And by writing down such distance functions, you specify the geometry of the surface. So, this is one of the few examples of geometries that we know exactly, where we can write down an analytic solution to understand and analyze the geometry. And this solution is called the Schwarzschild solution. So, when people started looking at this solution, and the first thing they realized was that this solution does a good job of describing the behavior of the earth in the gravitational field of the sun. That is because if you look far away, then the solution, by the way, just there is just one equation I want you to focus on, or one mathematical aspect here. This solution has some number which is r. Okay. So, what this metric is roughly telling you is that you have some space time. In that space time there is some time, this t is for that time, and then there is some radial distance from some point. Okay. I will tell you what that point is in a minute, but just remember there is some coordinate here r. So, just remember this symbol r, which is roughly telling you the radial distance from some point, the radial coordinate from some point. Okay. So, what people realized first was that if you took this radial coordinate to be large, so you looked at the earth which was well away from where the mass of the sun was, this solution did a good job of describing the behavior of the earth in the gravitational field of the sun. But then when they looked more closely at this solution, they found that in fact it had some rather unusual properties. So, the rather unusual properties it has is that if you really take this solution seriously and you think that it defines for you some kind of fabric of space-time, then you find that the picture you get of this fabric of space-time is the following. You have some smooth region elsewhere. So, if you had the sun would be here and the earth would be somewhere in the smooth region. But then as you go closer and closer to this to this point where the mass exists, you find in fact that something rather remarkable happens, and rather than getting some smooth fabric of space-time, you have a tear in the fabric of space-time. And this kind of tear in the fabric of space-time is what is called a black hole. Okay. The sun is not a black hole because the sun does not really obey the Schwarzschild equation all the way. It stops obeying the Schwarzschild equation once you reach the Schwarzschild solution, once you reach the surface of the sun. Okay. So, the Schwarzschild solution really describes a point mass. It does not really describe the sun very accurately if you go to the surface of the sun. But if you took the sun and you were to compress it by a tremendous amount, as I will describe in a minute, then you would find that you would get this kind of a Schwarzschild solution, which would have not some smooth bump in the fabric of space-time, but rather a tear in the fabric of space-time. And there are two regions in this black hole that are very important and that I will refer to in this talk, and so try and keep track of these regions. One of them is the outer edge of this black surface. So, you see this, there is a black surface here. This outer edge is what is called the event horizon of the black hole. And then there is this tear, there is this part where things go down a lot, and that is the singularity in the black hole. Okay, that is really where the point mass is sitting. In this talk I am going to say very little about the singularity of the black hole. Okay, so, you can forget about this part where you have the singularity of the black hole, but remember this part where you have the horizon of the black hole. And the way you should think of the horizon of the black hole roughly is as a point of no return. Okay. So, it is the point where once an observer crosses this red to black interface and gets into this black part, there is no way for the observer to stop himself or herself from falling further down and reaching the end of the singularity. Okay, so, not even light can escape once you have crossed from this red to this black region. So, as long as you are far away, that is fine, but once you have crossed from the red to the black region, nothing in the world can stop you from falling all the way down to the singularity at r equal to 0. Okay. The second thing, which is a funny thing about the horizon, is in fact that locally the horizon is a very deceptive thing, because you do not quite know when you have crossed the horizon. It's like sometimes you have these whirlpools, so you have these currents in the river, And these currents are very deceptive. You know, you think you're swimming along and you think that there's nothing violent happening, but then suddenly you find you're at a point of no return. And the horizon is an object of that kind. If you have a big enough black hole and you were to cross the horizon, at the time that you cross the horizon, you wouldn't feel anything bad or special happening to you. But your fate is sealed, because after that you can't escape outside to ordinary space-time and you are bound to end up at the singularity. Okay? So, the way this is sometimes said is that horizons are global properties of the space-time, you know, but they are not local properties. In fact, we could be crossing the horizon of a big black hole right now and we wouldn't know it, except that our fate would be sealed and that there would be no way for us to get out of the black hole later. Okay? So, horizons are funny kinds of objects, and they are far away from the singularity, and they're like the boundary of the black hole. Okay? So, that is the way you should think of black holes. Okay. Now, when these black hole solutions were first understood, you know, people thought, okay, these solutions do a good job of describing the sun, and then they have these funny properties of having these horizons and these singularities, but you know, maybe these things don't really exist in the universe. But in fact, in the past a few decades, we've done a good job, and astrophysicists have done a good job, in fact, of finding a lot of black holes in the universe. So, we look around us, and everywhere we see a lot of black holes. This is a picture, it's a composite picture using spectrum from many different telescopes of a black hole in the center of our own galaxy. Okay. So, this is a black hole in the center of the Milky Way. It's not very far from us, from 26,000 light years away, and it's very massive. Okay. It's a giant, it's 4 million times as massive as the sun. Of course, you don't see the black hole itself. What you see is that there's a whole amount of stuff that's swirling and falling into the black hole. So, you see the stuff around the black hole, and this black hole, and what you see is that there's some gigantic object. It's gigantic because it's 4 million times as large as the sun. There's some gigantic object which is sitting at the center and swallowing up more and more stuff, and then you infer that it's a black hole. And these black holes exist everywhere, not just in our galaxy. Here's another picture from the Hubble Space Telescope. This is really very far away. It's 100 million light years away, and it's even bigger than the black hole in the center of our galaxy. This is a distant galaxy, and it has a mass that's 500 million times as massive as the sun. So, it's another gigantic black hole which is very far away, but it's very, very big. Not all black holes are this big. For example, this is a black hole which is just about, you know, a little more than 10 times the mass of our sun, and it's a black hole in our own galaxy. It's called GRS 1915. For naming conventions, I never understand. But it's a black hole which lives in our own galaxy, and it's about 40,000 light years away, and it's only 14 times the mass of the sun. This black hole, in fact, has an interesting aspect to it. You know, it's a rotating black hole. So, Schwarzschild black hole, the picture of the black hole I showed you was just some object which was just sitting at rest. This is a black hole that's kind of, you know, going around its own axis, and it's going around so fast that the surface, the horizon of this black hole is almost moving at the speed of light. Okay. So, this is a black hole which is very close to what is sometimes called the extreme limit of a black hole. Okay. And in fact, these measurements were done about 10 or 15 years ago, and they are very interesting measurements, and it's a theoretically a very interesting black hole because it's going around about with as much velocity as it could possibly have on theoretical grounds, about 98% of the angular velocity it could possibly have on theoretical grounds. Okay. Now, in fact, I should say that, one more thing I should mention, as I'm sure many of you have heard, in just about a year and a half ago, we also, you know, these black holes I was showing you are black holes you see in the X-ray and by using visible spectrum, by using radio telescopes. But now we have another way of looking at black holes, and that was a window that LIGO opened up for us in the universe. This is a picture of this LIGO detector, and the detection they made a year and a half ago was the gravity waves, these ripples in the fabric of space-time that I told you, that traveled from the collision of two black holes, and that, you know, these gravity waves come and they cause the arms of this detector to bend and stretch. And by causing them to bend and stretch, you can use that to detect these gravitational waves, and that gives you one more way of looking at black holes in the universe. So, I should say that the whole theory of how, before I come to this, the whole theory of how black holes are detected and observed is actually a very interesting theory. You know, many of my astrophysicist friends spend their time trying to infer the existence and detect the properties of these black holes. You know, in these past few slides, I told you all these numbers. I said, you know, here's some black hole that's going at 98% of how fast it could go, and you could ask me, you know, how do you know that it really is going at 98%? And that's actually quite an interesting and delicate astrophysical question, the question of how you measure all of these parameters of a black hole. But in the rest of this talk, I'm not actually going to talk about that question because theorists like me are interested in theoretical experiments about black holes which are very vanilla black holes, and that's because we are interested in black holes which are very simple black holes, where the only thing we want to think about is one star which is collapsed into a black hole, and then we don't want to think about all of this accretion disk and all of this other stuff, because that for us is an extraneous complication. Okay? So sometimes it's useful to focus on the simplest possible setup, and so I'm going to focus for the rest of this talk on these very simple black holes. So this is just a black hole where you had some star. Okay? It was a big star. It has to be, you know, larger than, it has to be slightly larger than our sun. And there's some star, and after this, the flames of this star die out, there's nothing to prevent this star from collapsing. So it starts collapsing. You see this dashed line, it becomes smaller. This dashed line is where the event horizon would be for that mass. And once it becomes smaller than the event horizon, as I said, there's nothing that can prevent it from collapsing some more, and then it just keeps collapsing more and more till it becomes a point. Okay? So this is the kind of process I want you to focus on, not all of those spectacular black holes I showed you that had all sorts of other astrophysical phenomena around them. This is just one poor dying star in some isolated part of the universe, and this star, you know, has ended its life, and after it's ended its life, it's too massive, and so it just collapses onto itself and it becomes a black hole. Okay? So we are going to talk about stars of this kind. So in fact, it's often not convenient to talk about cartoons of, you know, I showed you a cartoon on the previous slide. You had a star, and then I showed you what happened to the next stage of the star, what happened after some time. It's not convenient to have the sequence of pictures, so I'll draw sometimes these space-time diagrams. So this is the same process as what I showed you in the previous slide, but it's drawn in a space-time diagram. A space-time diagram, this is a diagram where you have time that runs on the y-axis, and you have some other radial coordinate that runs on the x-axis, and this is telling you the evolution of that radial coordinate with time. So you see you had some star that started out as a big star, it was capturing, you know, it occupied a lot of radial coordinate, and then as you go further it shrinks more and more and more till it basically shrinks to a point. Okay? And this is this magenta line is the event horizon, this dashed line that you see here. Okay? So once, if there was someone who was living on the star surface at the beginning when this collapse started, they were outside the event horizon. Okay? So they could have escaped. If they found out that now, you know, the star is going to collapse, they could have fired their rockets and escaped. Then the star starts collapsing, and once it has collapsed past its event horizon, it can't stop itself from collapsing. And if there's somebody who forgot to escape the surface of the star, they can't prevent themselves from getting crushed into this point-like singularity either. Okay? So this is an example of what's sometimes called a space-time diagram, where you just put time on the y-axis, and you put some other spatial coordinate on the x-axis, and you just, you know, evolution upwards is evolution in time. So I'll show you these diagrams, and if you haven't seen them before, don't get scared. There's nothing conceptually complicated about them.
May I interrupt for a minute? Can you give a sense of time? For example, the Datt-Oppenheimer-Snyder Collapse.
Yes.
When was this first formulated?
Oh, when was this first formulated? Good. This was done in 1930s. Actually, it was first done by a Bengali physicist called Datt. Although it's now
Misspelled.
no, actually, I think this is correctly spelled. He spelled his name as D-A-T-T. So that's I think, yeah, you know, yeah, that's how he spelled his name, not misspelled. And then, although the names that commonly associated with this are that of Oppenheimer and Snyder, who did this later than that. I may be getting the dates a little wrong, but I think it was the 30s. Yeah, I think it was the 30s. But don't hold me to that. I think that's about right. I mean, it's not within 10 years of that. Okay. So this is an old solution, and it's a solution which, you know, generalizes the Schwarzschild solution because it has a star. It tells you, you know, the Schwarzschild solution in some sense is the end point of this collapse. It's telling you what's happening up here when all of this star has gone off. I want to think of a slight generalization of that, where you had a star and you want to look at evolution in time of the star. Okay. Now, one more thing, let me introduce you to one more notion, which is that when we draw these space-time diagrams, it's often convenient to draw the diagram so that light rays are 45-degree lines. You see, because I said that one of the things that general relativity tells you is that space and time, notions of space and time can become very weird. and especially once you go past the horizon, they can become very unusual. And therefore, one way to understand what are called the causal properties of a space-time is to is to choose some other coordinates, choose some way of drawing the diagram, so that light rays become 45-degree lines. So that's what I've done. This is in fact yet another picture of the same process I showed you previously, where you have a star that's collapsing. You can't see the collapse so clearly here because the radial coordinate has got distorted, but that's a price I pay. But what I get as a result of that is that I get these light rays being 45 degrees. So you see the horizon here is a light ray, and that's telling you that even if you had a light ray here, once it's inside, it can never get outside. So the right side of this is ordinary space, and the left side of this is the interior of the black hole. And you can see that once you had a light ray here, there's no way for it to get outside, because light rays are 45-degree lines. Okay? If you're inside here, you can go outside, but if you're outside here, you can't come in. If you're outside, you can go inside, but if you're inside, you can't come outside. Okay? And that's the reason, in a sense, that horizons are things you can't escape from, because horizons are the trajectory of a light ray. Okay? So you see the horizon here is the trajectory of a light ray, and that's the reason you can't escape from a horizon, because the horizon is just like a light ray which has crossed you, and then you can never catch up with it once a light ray has gone past you. Okay. So I'll draw these diagrams, and don't get worried about them. It's just basically time on the y-axis and some radial coordinate on the x-axis. Okay, good. So now I've described to you this black hole, and now my giant is back. And the kind of experiment I want to think of, the thought experiment I want to think of, is that this giant comes in and the black hole is formed. This black hole I told you, it's formed, and then the giant comes in and he takes the Earth or something else, maybe a library or some the college or all of us, and he rolls us into this ball and he pushes us into the black hole. Okay? So once the black hole has formed, you can then try and perturb the black hole. You can do addition, you can play games with the black hole. Of course, we don't have the technological ability to play these games right now, but in principle you can think of experiments where you would play games of this kind. These are what are called thought experiments. And so let's say you throw in some additional matter into the black hole. Now people started understanding what would happen if you throw in this additional matter. Of course, what would happen is that the black hole would eat up this additional matter that went in. Black hole has an insatiable appetite. It eats up whatever you throw into it, and it would grow a little. It would become a little fatter. Right? You throw in some stuff, it grows and becomes a little fatter. And so here's another picture. As I said, instead of thinking, it's useful to draw things in terms of space-time diagrams. So here's my black hole which formed, and here's this orange line. This is the trajectory of this additional object that I threw in. Of course, what happens, the object ends up at the singularity because it falls into the black hole, so it gets crushed like this original star got crushed. This line is the singularity, and the horizon grows a little bit. Right? So there's nothing so complicated about what happens. Well, then when physicists started analyzing in quantitative terms what would happen if you did experiments of this kind, they found that there were some laws you could write down for experiments of these kinds. And in fact, these laws turned out to be very similar to the laws of thermodynamics. So it turned out that if you threw in some matter, so this is dm, if you change the mass of the black hole by throwing in some matter, then the area of the horizon would change. This is dA, this is the change in the area of the horizon, and there's some constant of proportionality between them. And what is more, you can never reduce the area of the horizon of a black hole. That's roughly because you can't suck out matter. In fact, that's not precisely why it's the case, because in some situations you can reduce the amount of energy in a black hole, but you can never reduce its area in a physical process. Okay? So sometimes you may be able to suck out some energy out of a black hole, but you can never reduce its area. And that actually is very similar to some laws of thermodynamics that perhaps many of you have already seen in your school or college syllabi, and that tell you that if you throw in if you have some isolated system, you can do various experiments with it, you can add energy, you can remove energy, you can do various things, but the change in the internal energy of the system is given by the temperature into the change in the entropy, and then there are these work terms, there are these PdV terms, or if you have chemical potentials, you have other kinds of potentials, there are other work terms that come along with it, but there's some rule that relates the change in the internal energy to the change in the entropy plus work terms. And there's a second law of thermodynamics which tells you that if you have an isolated system, there is nothing you can do to reduce its entropy. And in fact, this is the second law of black hole dynamics. So by thinking of the kind of Jadankian experiments that I described, where you took a black hole and then you throw matter into it, or you do various other manipulations of the black hole, people found that there were these laws of black hole dynamics that were very similar to the laws of thermodynamics. Okay, so in a sense, these black holes which are these, you know, abstruse objects, they are galactic objects, they are things which you think of as being some giants that sit in the universe, obey laws which are very similar to the laws of, you know, just some cup of coffee, ordinary things that we see around us. Okay. So, the laws of black hole dynamics are similar to the laws of thermodynamics that we think apply to all sorts of things, okay, to water, to hot objects, to experiments we do in our lab. And black holes obey the same set of equations if you think of black holes and you try and perturb them. Now, for a while people thought that this was just a formal analogy. You know, if you look at the Feynman lectures in physics, Feynman has a section where he says the same equations have the same solutions. So, this often happens in physics that, you know, you get the same set of equations in two different systems. You look at a spring and a simple harmonic oscillator, some mass moving on a spring, and you look at some electrical circuit which has an inductor and a capacitor, and the equations of these two things are the same. Okay. So, it often does happen in physics that you get the same equations in different physical settings, and so people thought for some time that this was an example of that kind, where for some reason you have these laws of black hole dynamics, they happen to look like the black hole, like the laws of thermodynamics, but okay. In fact, in the 1970s, the British physicist Stephen Hawking found that this wasn't just a formal analogy, that in fact you should really associate a temperature with black holes, and he calculated the formula for the temperature that you should associate with black holes, and it turns out to be this, okay, where h bar is the Planck's constant, c is the speed of light, g is Newton's constant, and k is Boltzmann's constant, and m is the mass of the black hole. The only parameter here is really that depends on the black hole is the mass of the black hole. Okay. Everything else is constants. So, you should really think of T as 1 over the mass of the black hole. Okay. So, you have a more massive black hole, it is colder, it is associated with a smaller temperature. And Hawking found that you should really associate a temperature, and so this analogy between the laws of thermodynamics and between the laws of black hole dynamics was not just a formal analogy, but there was really something physical. Black holes really had a temperature, and the reasons they were obeying these laws of black hole dynamics was because they really were just simply the laws of thermodynamics in a disguised form. Okay, so that was Hawking's discovery. Let me just try and give you a sense of how Hawking's argument went. I won't derive this formula, of course. What Hawking said is that, you know, if you think of this black hole and there's a horizon, there's an event horizon of the black hole, and you think of quantum effects in the black hole. So, it's very important that this formula is a quantum formula. If you think of quantum effects in the black hole, then these quantum effects will cause spontaneously in space-time particles and antiparticles to form near the horizon. But if you have such spontaneous pair creation near the horizon, then the guy that's inside the horizon will fall into the singularity, while the guy which is outside the horizon will come out. So, you can look at this right hand side picture which zooms in on this part. You see, you have this pair creation, this blue and green particles that are created in a pair. This is just a vacuum fluctuation, but then the one which is inside the horizon falls into singularity, because that is the fate of everything that's inside the horizon, and the one that's outside escapes outside. And so, if you have an observer who's sitting far away, it looks to him like you have a steady stream of particles coming out of the black hole, but really this is just happening because you have these vacuum fluctuations near the horizon of the black hole. Okay. In fact, Hawking was able to use this to derive the formula, and so here's another picture of what it looks like. You see, if you add quantum effects to a black hole, then the old picture you had of a black hole, remember we said there was a black region and then there was a rent in space-time, is modified, and rather now quantum effects start what one might call a quantum fire at the horizon of a black hole. So, you have a black hole, you have something from general relativity, you add in quantum effects and you start a quantum fire at the horizon of the black hole. I have exaggerated the fire a lot in this picture. In fact, it is a very weak fire because it is a quantum fire. But nevertheless, once again, you know, from a philosophical point of view, this is going to be important. From an in principle point of view, it's important that you start this fire on the surface of the black hole. Okay? And when you talk about the temperature of this fire, what you really mean is that you look at the spectrum of particles that comes out from this fire. Okay? So, the fire has a color. Spectrum is just a fancy word for color. Everything around you has a spectrum, and if you have you know, a spectrum of particles that's coming out of this fire, and you look at the distribution, the power that lives in, this is a graph of, you know, how much power is emitted in wavelengths, okay? And you have a distribution of this, and it tells you that this distribution obeys what's called the Planck distribution, and this Planck distribution is controlled by one parameter, which is the temperature, and that's how you define the temperature of the black hole. By looking at the emission spectrum of the black hole and by fitting that to the Planck spectrum, and so you come back to this formula for the temperature. Okay. Now, it is useful to put in some numbers for this formula for the temperature. Remember, I said it is a very weak fire, and in fact, if you have a black hole of the size of the sun, the temperature of that is just 10 to the minus 8 Kelvin. Okay. So, if you really took the sun and you made it into a black hole, you would get a black hole whose temperature would just be 10 to the minus 8 Kelvin. Okay. If you wanted, remember, but the temperature goes inversely proportional to the mass. So, if you want to get a hotter black hole, what you need to do is take a smaller object and turn it into a black hole. Okay. So, it is useful to keep just order of magnitude numbers in mind. I do not know if you can see at the back, but this is 6 into 10 to the minus 8. Okay. Now, so let us follow this a little further. You see, you started a quantum fire, it is a weak fire, but as I said, we want to think of a black hole which is just living isolated somewhere in the universe, and we have all the time in the universe to look at this black hole. So, now you have this black hole, and of course, the energy in the black hole, as all of you know, one formula which everyone knows, is just proportional to the mass of the black hole, right? It is E is mc squared. So, that is the total energy that lives inside the black hole, but this energy is lost constantly, and it is lost precisely, and you can compute the rate of loss of this energy by using the same Stephen-Boltzmann law that you have used and you have seen even in high school physics. Okay? And that tells you that the loss of energy is proportional to some constant and is proportional to t to the 4 and the area of the object that is radiating. Okay? That is the rate of the loss of the energy. So, dE by dt is some constant into t to the power 4 into the area. You can convert this into the mass. Remember, the area goes like the square of the radius goes like the mass. So, that is a factor of m squared, but the temperature goes like 1 over the mass. So, that is a factor of 1 by m to the 4. So, you find that the rate of loss of the mass, because you see energy is proportional to mass, is proportional to 1 over the mass squared. Okay. So, if you take Hawking's calculation and you push it forward a little bit, it tells you the rate of loss of mass is 1 over the mass squared, okay, with some constant which is roughly 4 into 10 to the power 15 in SI units. Okay. Okay, so now you can follow this a little further. You can say, well, what if you just wait for long enough? If you have some object, it's losing mass by means of radiation. What will happen eventually, if everything around is at absolute 0, it will just radiate everything away. And even if everything around is not at absolute 0, provided it's hotter than things around, as this black hole radiates, it loses mass and becomes even hotter. Right? So, it's unusual compared to other objects in that as it radiates, it becomes hotter. Okay? So, it has a negative specific heat. And so, this black hole, you wait for this, and this black hole radiates this mass, and after a while it evaporates completely. Okay? And so, the black hole has a lifetime. The fact that the black hole has a temperature due to quantum effects tells you also that it has a lifetime, and this lifetime is proportional to the cube of the mass, okay, with some constant that looks like a small constant. So, if you had a mass of 1 kg, then this black hole would evaporate, in a time which was 10 to the minus 17 seconds. But if you take a black hole which has the mass of the sun, which is 2 into 10 to the 30, then this lifetime is much longer. Okay? In fact, this lifetime for something like a solar mass black hole is 10 to the 67 years. Okay? This just comes by putting that into the formula. So, effectively a black hole like that of the sun is eternal. Okay? So, you do not really need to worry about a big solar mass black hole like the one in the middle of our galaxy evaporating. It is effectively eternal, because remember, the age of the universe is only about 13 billion years, which is about 10 to the 10 years. That is much smaller than this number. Okay? So, solar mass black holes are effectively eternal, but if someday, of course we do not have it today, if someday you had some technology to create black holes out of objects that were much smaller, if you were to take a big plane, okay, a Boeing jumbo jet, and you were to take that jumbo jet which has a mass of about 400 tons, and you were to do something to it to squeeze it into a black hole, then that black hole would evaporate in 5 seconds. Okay, so, it would take that 400 tons and convert it entirely to radiation in a period of time 5 seconds. Okay. So, if you want to think about these questions physically of black hole evaporation, you shouldn't really think of solar mass black holes. You should think of ordinary objects. If you took this room and some enormous force came and compressed all of us into a black hole, we would evaporate pretty fast. Okay, we would evaporate in the order of a few seconds. Okay, good. So, now here is the story we have come up with. Now, I am coming to the point of the talk. You see, this is the life of a dead star. So, you have a star, it was alive and thriving and had putting out energy, but then after a while, the star died and then it collapsed into a black hole. Once it collapsed into a black hole, quantum effects started a fire about the black hole, and then the black hole evaporates once you wait long enough, it evaporates and it gives out this radiation, right. So, this process of black hole formation and evaporation looks like it converts a star into thermal radiation. Okay. If you followed the story so far, that is what I have told you. Now, you might say, why is that a problem? Well, it is a problem because it gives you the following kind of flow chart. It says you had star 1 and star 1 collapsed into black hole 1, star 2 collapsed into black hole 2, but remember something I said, which was that the black hole radiation depends only on the temperature, and the temperature only depends on the total mass of the star. Okay. So, this was an important fact that I mentioned. The temperature of the black hole depends only on the total mass of the star. So, if these two stars had the same mass, they would give you the same eventual radiation, right. So, it looks like starting with one kind of star which might be made out of some kind of element, and another kind of star which might have some different astrophysical properties and different features, you could form them into a black hole and you would end up with the same radiation. And this suggests that these time evolution arrows can't be reversed. And if that is really correct, that would be a catastrophe. It would be a catastrophe because the reversibility of time evolution is a fundamental property of both classical and quantum physics. You see, if you take a ball and you throw a ball from this side to this side, if you reverse at every point its position, its velocities, it will go the other way. If you tell me the position and velocity of the ball at this time, I can predict not only where it will go, but also where it came from. You see, we often use physics to try and predict what will happen in the future, but you can also use physics as well to retrodict. Physics works as well forward in time as it works backward in time. And that is clear from the form of the equations that you solve. The form of the equations you solve in classical dynamics tell you that there is some rate of change of momentum that is proportional to some force, but this differential equation you can solve forward in time or backward in time. Similarly, in quantum mechanics you have what is called the Schrödinger equation, and the Schrödinger equation you can solve forward in time or backward in time. Okay. The details of these equations are not important. The principle is simply that given the state of the world at one instant, you can retrodict as well as you can predict. Okay. You always have one-to-one evolution. Evolution is a map which goes from one state to one state. You never have two distinct states evolving to the same final state. That would violate the reversibility of time evolution, which would be a catastrophe for quantum mechanics, which is after all what we use to derive all of these formulas about the Hawking radiation and the evaporation of the black hole and so on. Okay. So, this is what is called the information paradox. It is the statement that the radiation of a black hole looks like it depends only on the total mass of the black hole and not on the constituents that made up the black hole. And if that is the case and you allow the black hole to radiate long enough to completely evaporate away, then it looks like you could get the same final radiation starting with two different constituent black holes, and that violates the reversibility of time evolution, which is in complete contradiction with everything else that we know about physics. Okay. So, this is what is called the information paradox, and it has been with us for several decades now. Okay. Okay. So, I hope that all of you when you leave this room will at least understand this part of what the paradox is. Okay. I am now going to go on and talk about some more recent work. I will talk about some work of my own on resolutions to this paradox that we have been working on. What I will talk about now is more recent, not also some parts of what I will say are speculative, but I would like all of you to understand at least this part of this is what the information paradox is. Okay. Okay. So, now I am going to describe to you some resolutions that we have been developing to this paradox. These resolutions are things which we have developed with many collaborators, including my students at ICTS, Sudeep Ghosh, Pushkal Srivastav, a very close collaborator at CERN, Kyriakos Papadimos, and his students there. Okay. So, let me try and tell you now what the resolution to this paradox is. I hope the paradox is clear. Okay. The paradox is that you start with two different black holes, they both form by different stars. After they form, they radiate. The radiation depends only on the total mass or nothing else. Therefore, in the end you get the same radiation from both the black holes, and that is in contradiction with reversibility. Okay. So, it is a simple enough paradox to state. Okay, good. So, now here is a possible resolution to this. Possible resolution to this is as follows. So, imagine that this is a black hole, okay, and the black hole has emitted some photons. These are photons of different colors. Remember I said you look at a black hole and you look at the spectrum of photons that it emits. So, here are some photons, it's emitted photons of red, yellow, blue and purple. This is not really, black holes emit in a completely different spectrum. They don't emit in the visible spectrum unless you have designed a black hole to have that kind of temperature. But let's say we had a black hole which emitted in the spectrum, and this set of dots is actually placed entirely randomly on the screen. So you might think that in fact there is no information in this radiation, right, because you have some random set of photons. I really generated this using a computer program, just randomly place some dots of different colors, and in fact there are as many red dots as there are blue dots, as there are purple dots, as there are yellow dots. Okay? So there is just some random spectrum, and you might think the spectrum contains no information, because if you look at any given color, it looks like it's completely randomly placed. If you look more closely, you find that there is some information. Information is as follows. Everywhere you have a purple dot, if you draw the line to the black hole and a line on the other side, you will see you have a yellow dot. And everywhere you have a red dot, if you draw the line to the black hole and continue it on the other side, you will see you have a blue dot. Okay? This is an example of what are called correlations in random data. Okay? So there are, even though this data looks like it's random, it's not really random, because there are delicate correlations between different photons. Okay? So the information contained in the sum total of all the photons is more than the sum of the information contained in individual photons, and that's because there are correlations in the data. Okay? So these correlations can actually preserve information that went into the black hole, even if it looks like the emission spectrum of the photons is random. Okay? In fact, you can estimate how small these correlations have to be, and it turns out that these correlations can be very small and can still contain a lot of information, because there are so many photons that are emitted from the black hole. In fact, it turns out these correlations can be suppressed by the entropy of the black hole. So remember, I said the black hole has a temperature. Just like it has a temperature, it has the entropy. If you forget about the Boltzmann constant, the entropy is just a number, and that number is this. It's 10 to the 16 into the mass of the black hole in kg squared. So even if you take a black hole of 1 kg, that already has an entropy of size 10 to the 16. If you took this black hole of 400 tons we were talking about, that would already have a very, very large entropy, and these correlations can be as small as exponential, as in the negative exponential of this number. Okay? So for this 1 kg black hole, these correlations could be e to the minus 10 to the 16, and they could still contain enough information to preserve information. Okay? So the slogan is that very delicate correlations in a very large number of photons can preserve a lot of information, and what we argued is that this was in fact enough to preserve all the information that went into making up the black hole in the first place. Okay? Okay. Now, but in fact that can't be the end of the story, because even if we say that there are these very delicate correlations, we have to explain how these correlations form. Right? Because it looks like you compute this spectrum of radiation, it looks like you get some random photons. Now we are saying, well, they are not quite random, they are actually delicately correlated. One photon, if it went off slightly in this direction, then the other photon would have gone off slightly in some other direction. And if you looked at the sum total of everything that, all the radiation that came out of a black hole, you would see all of these delicate correlations. And then someone would ask, how do these correlations form? And the reason that's an important question is that if you look at the black hole, remember something I tried to emphasize to you is that the radiation that comes from the horizon of the black hole. But the matter, the stuff that made up the black hole is sitting somewhere else. It's already fallen into the singularity. So, but this radiation is coming, this is this particle, antiparticle falling in, and the particle that's falling out is coming from the horizon. So how can even these very small delicate correlations reach here? How can this information reach the horizon to get even these delicate correlations between these different particles? Okay? And in fact it turns out that let me just say one more thing. You see, one thing you might have thought is that maybe these correlations don't form when the black hole is big. As the black hole evaporates, it becomes smaller and smaller, and eventually the black hole itself becomes almost point size, and maybe that's when all the correlations form. But in fact that can't be the case, because if you look at the amount of information that's contained in this radiation, this information comes out at a pretty steady rate after about half the black hole has evaporated. So this is a plot of something called the entropy of the radiation. For those of you who don't know that, you don't have to worry about that. Think of this as roughly a part of how much randomness there is in the radiation that's emitted. So in the beginning everything is very random, but then these correlations start to take over, and you can argue that things become pretty less and less and less random once about half the black hole has evaporated, and very soon they go back to being completely not random, because that's what they have to be if you want to preserve all the initial information that went into forming the black hole, which wasn't random at all. Right? So it turns out that that means that information can't come out right at the end of black hole evaporation. It has to come out, well before the end of black hole evaporation, while the black hole is still large. So the way that works is, in fact, that you say that in this theory, that in fact, even though the matter is far away from the horizon, with a very small amplitude, which is given by e to the minus entropy of the black hole, this matter communicates non-locally with the horizon. Okay. So you see that we've introduced some non-locality back into the theory that we tried to get very hard to get rid of when we came in the theory of general relativity. And the claim is that there is some very small amplitude for these non-local correlations between where the matter is and the horizon of the black hole. And you can quantify how small this amplitude has to be for information to be preserved, and it's suppressed by e to the minus s, where s was this large number which was related to the entropy of the black hole that I told you about. Okay. In fact, you can say something slightly stronger, and what you can say is as follows. You see, when you in physics and in these field theories, you often try and quantify what lives at some point using some degree of freedom. So this could be some property of the space-time at that point, some say the curvature of the space-time. So in fact, this statement of non-locality goes a little further. It says if you think of this phi as being some measure of the space-time at this red point inside the horizon. It says if you want to make a measurement of this, or some curvature, or some property of the interior of the black hole, you could get away by making a lot of measurements of some property outside the black hole, on these red dots outside the black hole, but a very large number of them, s of them, where s was this entropy, and then constructing some very complicated polynomial out of these measurements, and that would also give you information about what was happening inside the black hole. You see, if this is true, it's even for those of you who don't follow field theory, this is actually a very remarkable statement. It's a statement that if I want to make a measurement at the position of this bottle, then rather than making a measurement at the position of this bottle, I can make some measurements of positions around this bottle, and that would be enough to tell me what's happening at the position of the bottle itself. So you see, that's in complete violation with our everyday intuition. And indeed, these are kinds of things which happen only in very extreme circumstances. You have to make a lot of very, very fine measurements, and so this is not something you would see in everyday life. But you see, once again, philosophically, this is something which is violating your everyday notions of locality that you started with. Okay? So in fact, this is not something which is totally in the air. It's something you can actually make mathematically precise in some toy models of quantum gravity. So not yet for the real black hole, but if you think of some toy models of quantum gravity, these are roughly quantum gravity. If you think of some toy models of gravity in a box, so rather than thinking of gravity in a universe which is unbounded like ours, we think of gravity in some box. Okay? So if you think of gravity in a box, that's what's called gravity in anti-de Sitter space. In fact, in that setup, you can prove that if you want to make a measurement in the middle of this box, so this is again a space-time diagram, time goes up. At one time, you want to make a measurement of this blue dot. You can in fact get away by making measurements on the boundary of this box on these red dots. Okay? But you have to make a lot of measurements. The number of measurements you have to make is roughly the ratio of the size of the box to the Planck scale, okay, which is a very, very large number. But if you do that, you can actually get all the information that lives at the center of the box by getting information from the sides of the box. And this is the kind of thing that's necessary if information has to be preserved in Hawking radiation. Okay, so let me just end with some pictures and some speculations. You see, we don't yet have a way of understanding how this works in our universe, but if it works in our universe, we believe it should work in the same way, okay? In that you have information at some point, and to get information at this point, you can in fact make a number of measurements at a large number of points that surround this central point, and you should be able to get information about the central point, provided you make a sufficiently large number of measurements. This is an idea that's sometimes called complementarity in the literature. Okay? And it's something that works, which we know works in anti-de Sitter space if you have some toy models of gravity, but we believe should work also in our universe. Okay? And in fact, if you believe this picture, and as I said, we don't even have a complete mathematical formulation of how this would work in our universe, only how it works in toy models of gravity, then once again the picture that you get of space-time is very different. You see, we started with a picture of having a fabric of space-time. But the fabric of space-time has the property that it's a continuous fabric. You see, one part of the fabric is independent of another part of the fabric. But if you believe this picture, then the picture that you get is slightly different. The picture that you get is more like saying that you have not a continuous fabric, but rather you have threads of space-time. Okay? So, you shouldn't take this too seriously, it's slightly misleading, but it's a good way to think about it at first order. It's the statement that in this fabric of space-time, which you thought was a continuous fabric, you really have these threads of space-time. And you see, one property of the threads is, if you're sitting on a circle here and you have all the threads in your hand, then you also know what's happening at the center of this fabric, right? If you control all the threads here, you also control what's happening here without ever having to go there physically. Right? Another thing you can see, another difference you can see is that the information content of the fabric is proportional to its area in this picture. But if you really had this picture of threads, the information content of this would be proportional to the perimeter, not to the area. Okay? And in fact, this is indeed something that you again see in toy models of gravity. So, let me just summarize what I said. What I've been saying so far is that you have this information paradox, and then to resolve the information paradox, you say that the information paradox is resolved by saying that the radiation that comes out of a black hole is not really random, but rather it has these very delicate correlations. And then in these very delicate correlations, you have to ask, what is the physical mechanism by which they form? And if you try and understand this physical mechanism in some toy models of quantum gravity, what you find is that this physical mechanism that forms these correlations in the photons that are emitted from a black hole actually involves slightly non-local effects. It involves effects which are very, they're effects which are non-local, that you would never see them in everyday life, but yet they're there, and in principle these non-local effects modify the picture of space-time that we have away from being a continuous fabric to thinking about these threads. Okay? So, in a sense, you see, we've come halfway back to where we started from. You see, we started with this idea of Newton's law and action at a distance, and then we said, well, we don't like action at a distance. We don't like action at a distance because we don't like non-local theories which have particles interacting at a distance, and therefore we invented this fabric of space-time to mediate the force between these objects. But then when we took this theory of the fabric of a space-time and we started pushing the theory more and more, we found the theory had black holes. Then we found that black holes emitted quantum radiation. Then we found that the emission of quantum radiation led to a paradox. Then we had to resolve the paradox, and to resolve this paradox, we've come back now to a picture of threads of space-time, which are again, somewhat slightly non-local. So, we've come not all the way back, of course, we still do have locality to an excellent approximation, and once again, as I said, these are very, very delicate effects. They're not effects you would see in everyday life, but from a philosophical point of view, we've come back a little bit back to where we started from, some picture of non-locality. Okay, so as I said, this is a theory that needs to be developed more, and maybe some of you in this audience will help to develop it, and so I'll conclude with this slightly speculative note, which tells us about how, in a sense, by thinking more about these interesting theoretical setups, our philosophical pictures of the universe are constantly evolving, and hopefully they'll continue to evolve in the future. Okay, so I'll stop.